Colonel John Kerkering stands inside a tunnel carved 30 feet beneath Greenland's ice sheet, watching frost form on the steel casing of a portable nuclear reactor that took 6 weeks to drag here on sleds. The ice is compressing his base at 4 feet per year, and there is no blueprint for what happens when it catches up. Around him, the walls are closing, 6 inches narrower than last month, and the ceiling has dropped 3 inches, squeezing inward under the weight of 6,000 feet of glacier pressing down from above. The reactor cannot be moved without 60 days of disassembly, and the ice will not wait that long. Earlier that spring, May 1960, Kerkering assumed command of Camp Century, 150 miles inland from Thule Air Base, where 85 Army engineers and civilian contractors lived in prefabricated buildings inside tunnels 30 feet below the ice surface. The base was invisible from above, covered by white canopy painted to match the glacier, so reconnaissance satellites saw nothing but unbroken snow. His orders were simple: maintain operational readiness and prepare for the next phase, a classified expansion the Pentagon called Project Iceworm. The PM-2A portable nuclear reactor sat in a separate trench, 40 feet from the main living quarters, generating 1.5 megawatts of electrical power and enough steam heat to keep the tunnels at 50 degrees Fahrenheit, despite exterior temperatures of -40. It was the only reactor of its kind ever deployed under ice, designed by the Army to prove that nuclear power could sustain a remote base without fuel convoys. The reactor hummed steadily, neutron flux controlled by boron rods, coolant circulating at 1,800 gallons per cycle. The reactor had arrived in pieces over 6 weeks during summer 1960, hauled by sleds across 138 miles of ice sheet. The heaviest components weighed 30,000 pounds, the maximum sled capacity, and were bolted together by welders working in insulated gloves. Each sled was pulled by a Caterpillar D8 tractor crawling at 2 miles per hour, because faster speeds fractured the snow crust and bogged the convoy. Engineers of the 21st Engineer Battalion logged every mile, checking load straps every hour, knowing a single cracked pressure vessel would contaminate the ice with no cleanup possible. Swiss engineer Peter Bucky's trench crew operated the experimental Peter Miller rotary saw, a 12-foot diameter blade mounted on a tracked vehicle, cutting arched tunnels 15 feet wide and 20 feet tall through compressed ice. The saw had never been tested in polar conditions, and there were no backup blades on Greenland. Bucky's crew worked in 2-hour shifts because the vibration numbed their hands, carving the tunnel network 100 feet per week, shaving the ice into powder that was blown out by diesel fans. Supply convoys from Thule ran every 2 weeks during summer, delivering fuel, food, and reactor components. Winter supply runs were impossible due to ice storms and zero visibility. The crews stockpiled 6 months of diesel, canned rations, and spare parts, gambling that nothing critical would fail between October and April. Each convoy was a calculated risk. Whiteout conditions could strand tractors for days, and frostbite could set in within minutes if a vehicle broke down. Kerkering's mission brief was, maintain operational readiness for Project Iceworm, the classified plan to install 600 Minuteman nuclear missiles in vertical silos beneath the ice, each aimed at Soviet targets 3,000 miles away. The missiles would be invisible to reconnaissance, immune to preemptive strike, and able to launch through 20 feet of ice using explosive charges. Camp Century was the proof of concept, demonstrating that men and machines could survive under the glacier long enough to build the largest hidden missile field in history. Glaciologists from the Army Cold Regions Research and Engineering Laboratory measured tunnel deformation every month using steel pins driven into the walls. By October 1960, the main tunnel had narrowed 6 inches, and the ceiling had dropped 3 inches. The pins were bending inward, metal groaning under the pressure, and the scientists logged the data without comment because no baseline existed. No one had ever tried to hold a tunnel open inside a flowing glacier. The ice sheet behaved as a plastic solid under pressure. It did not crack like ice cubes. It flowed like cold honey, squeezing inward at a rate determined by the overburden weight of 6,000 feet of ice above. The glaciologists explained that below 100 feet depth, ice crystals slide past each other without fracturing, a process called creep, and nothing could stop it except removing the weight, which meant removing the entire glacier. Kerkering's crew tried to slow the compression by recutting the tunnels with Bucky's saw, shaving the walls back to their original width. The saw roared for 12 hours straight, spitting ice powder into the ventilation ducts, and the tunnel was restored to 15 feet. 8 weeks later, it had closed again, the ice squeezing inward as if the saw had never touched it. The crew realized they were not building a base, they were fighting a glacier, and the glacier would win. The reactor trench was deforming faster than the living quarters because it had been cut deeper to isolate radiation. The walls were converging at 8 inches per year, and the steel reactor casing could not be moved without disassembly, which took 60 days and required the reactor to be shut down and cooled. Kerkering ordered monthly surveys of the trench, and each report showed the gap shrinking. If the ice touched the casing, thermal expansion would buckle the steel and rupture the coolant lines within hours. Army engineers calculated that if the reactor trench collapsed before the core could be extracted, the casing would rupture, releasing radioactive coolant into the ice, with no containment and no method to excavate it during winter. Standard construction solutions, steel bracing, concrete lining, could not be installed because thermal expansion from the reactor heat caused any rigid framework to buckle and shear within weeks. The heat that kept the base habitable was the same force tearing the support structures apart. The only option was continuous recutting, but the Peter Miller saw had no spare blades on site, and the manufacturer in Switzerland could not deliver replacements until spring airlift season. Bucky's crew inspected the blade every morning, looking for stress cracks in the carbide teeth, knowing a catastrophic failure would leave the base unable to maintain the tunnels. The saw was not a tool. It was a single point of failure, and there was no backup. February 1963. Glaciologist James Bender reported that the main tunnel had compressed 14 inches in 3 months, triple the expected rate. Ice flow was accelerating as surface snow accumulation increased overburden weight, and the mathematical models the scientists had built in 1960 were no longer holding. Bender's voice was calm when he briefed Kerkering, but the data was unambiguous. The base had months, not years, before the tunnels became impassable. Bucky's crew attempted an emergency recut of the reactor trench, but the Peter Miller saw blade hit a dense ice lens, a layer of refrozen meltwater harder than the surrounding snow ice, and a 6-inch radial crack appeared in the carbide-tipped cutting edge. The operator shut down the saw immediately, and Bucky knelt beside the blade, running his fingers along the fracture. He knew what Kerkering would ask, and the answer was no. There were no replacements, and the crack would only grow. The crew welded a steel patch over the crack and continued cutting, but the saw now vibrated violently and could only operate at half speed. A full trench recut that used to take 5 days now took 12. Kerkering watched the blade wobble as it bit into the ice, and he did the math. 12 days to cut, 8 weeks before the tunnel closed again, and the reactor trench was already narrowing faster than the main corridors. The margin had evaporated. Kerkering calculated that the reactor trench would narrow to unsafe clearance, less than 18 inches from the casing, within 90 days. Evacuation of the PM-2A required dismantling the core, loading it onto sleds, and transporting it to Toul, a process that took 45 days in summer and had never been attempted in winter. He briefed the Pentagon via encrypted teletype, spelling out the timeline and the constraint, and waited for orders that would decide whether they fought the ice or abandoned the reactor. Camp Century's single ice runway was rated for C-130 Hercules cargo planes only above -50 degrees Fahrenheit. Below that temperature, the ice became brittle and fractured under the landing gear load of 155,000 pounds. The runway crew had carved the strip during summer, smoothing the surface with graders and marking it with flags. But no one had tested a winter landing because the manual said it could not be done safely, and the Air Force would not risk a plane to prove otherwise. March 1963. Pentagon ordered Kerkering to begin phased evacuation, prioritizing reactor components and classified Project Iceworm silo plans. Personnel would be extracted in 2 waves, but the timeline depended on weather windows that might not open until April. The order acknowledged that winter evacuation was outside normal operating procedure, which meant the Air Force was gambling a C-130 and its crew against the chance that the reactor trench would collapse first. Kerkering read the message twice, then called his logistics officer. The first test landing attempt in late March cracked the runway ice. The C-130 touched down at 120 knots, and the pilot felt the surface give beneath the main gear. He aborted immediately, throttling to full power, and the plane clawed back into the air, trailing a 200-foot trench where the ice had fractured and collapsed. The loadmaster radioed Thule that winter landings were not viable, and Kerkering was back where he started. No evacuation, no timeline, and the ice still closing. The Greenland ice cap is not a static block. It is a glacier flowing toward the coast at 10 to 20 feet per year, driven by gravity acting on 6,000 feet of compacted snow that weighs 55 pounds per cubic foot. Under this overburdened pressure, ice below 100 feet depth deforms plastically through a process called creep. Individual ice crystals slide past each other along molecular planes without fracturing, causing the entire mass to flow like a very slow liquid. The weight above Camp Century was 15 million pounds per square foot, and no structure could resist it indefinitely. Camp Century's tunnels interrupted this flow, creating a stress concentration, like squeezing a balloon around a pencil, and the ice responded by flowing faster into the void, compressing the tunnel at a rate proportional to the depth and overburden weight. Recutting the tunnels did not stop the flow. It only reset the geometry temporarily, and each recut removed structural support, making the next collapse faster. The tunnels were not holding space open. They were creating a wound in the glacier that the ice would always heal. The PM-2A reactor could not be moved intact because the neutron-shielding lead casing weighed 42,000 pounds, over the Sled limit, and disassembly required cooling the uranium core to below 200 degrees Fahrenheit for 30 days, draining 1,800 gallons of pressurized water coolant, and unbolting the reactor vessel from its concrete foundation. Any attempt to move the reactor while hot would cause thermal shock, cracking the pressure vessel and releasing steam contaminated with fission products. The reactor was designed to be portable, but only after a shutdown sequence that took longer than the ice would allow. Runway ice failed below -50 degrees Fahrenheit because thermal contraction created microscopic fractures that propagated under point loads. When a C-130's landing gear, 16,000 pounds concentrated on 4 square feet, contacted the surface, the ice shattered in a cone-shaped failure zone extending 10 feet deep. The fracture propagated faster than the pilot could react, and once the gear broke through, there was no abort. The plane would sink into the void beneath and be crushed by the closing ice. Project Iceworm missile silos would have failed for the same reason the tunnels collapsed. Ice creep would deform the vertical shafts by 3 to 5 degrees per year, and a Minuteman missile must remain within 1 degree of vertical for gyroscope alignment. Beyond that tolerance, the missile tumbles on ignition, detonating solid rocket fuel inside the silo and releasing 400 pounds of burning propellant at 5,000 degrees Fahrenheit. No corrective mechanism existed. Hydraulic jacks could not push against flowing ice, and re-drilling the silo simply reset the deformation clock without changing the rate. Every proposed solution collided with the same physics. The ice was stronger than the structure, and time was on the glacier's side. Steel bracing buckled under thermal expansion and ice pressure. Concrete fractured in the cold. Hydraulic jacks had nothing rigid to push against. Recutting bought weeks, not years. The engineers at Camp Century were not incompetent. They were trying to solve a problem that had no solution, because you cannot build a permanent structure inside a material that flows faster than you can maintain it. April 10, 1963. The reactor trench ceiling sagged to within 28 inches of the PM-2A casing. Engineers estimated 12 days until contact, at which point the steel would buckle and rupture the coolant lines. Kerkering ordered the reactor shut down and began emergency cooling. But exterior temperatures were still -55 degrees Fahrenheit, and no C-130 pilot would risk a landing until the ice warmed to -45. The countdown had started, and the weather would decide whether they succeeded or died trying. Major William Failing, base logistics officer, proposed an alternative. Drag the reactor, still assembled, onto sleds and haul it across the ice sheet to Thule on tractors, a 7-day journey, gambling that the casing would not crack from vibration or thermal shock. Kerkering listened, then asked what happens if the casing cracks halfway to Thule. Failing had no answer, because a cracked casing would spread radioactive coolant across 138 miles of ice with no containment, creating a contamination trail visible from orbit and triggering an international incident with Denmark. Denmark owned Greenland and was never informed of Project Iceworm. The treaty allowed the U.S. to operate Thule Air Base for mutual defense, but it said nothing about nuclear reactors or missile silos under the ice. A contamination incident would expose the entire operation, force a political crisis with a NATO ally, and hand the Soviets a propaganda victory that would dominate headlines for months. Kerkering's orders were clear: protect the reactor and protect the secret. And if he could not do both, the secret came first. April 18. A weather window opened. Temperatures rose to -47 degrees Fahrenheit, and Kerkering authorized a test landing with an empty C-130, carrying only minimal fuel to reduce weight. The plane descended through cloud cover, landing gear locked, and touched down at 120 knots. The ice held, but the loadmaster reported hearing fractures propagating beneath the fuselage, a sound like distant gunfire, sharp cracks echoing under the floor. The pilot kept engines at idle thrust and took off after 4 minutes on the ground. Kerkering made the call: begin full evacuation, prioritizing reactor core components and classified Iceworm documents. Personnel would fly out in 2 waves, 40 per flight, with the reactor vessel left behind, drained and sealed, to be extracted during summer 1964 if tunnel conditions allowed. He knew the vessel would not be extracted. The tunnel would collapse long before summer. But the order gave his crew a reason to believe they might come back, and right now, belief was more valuable than truth. The crews worked in shifts, dismantling the reactor core and loading components onto sleds under deadline pressure. Each piece had to be drained of coolant, wrapped in insulated tarps, and strapped to sleds rated for 30,000 pounds. The work took 18 hours because the bolts were frozen and the gloves made fine motor control impossible. Above them, the trench ceiling sagged visibly, ice groaning as the gap closed inch by inch. No one mentioned the sound, because acknowledging it would mean admitting they might not finish in time. April 20th. The first C-130 lifted 40 personnel and half the reactor core components, engines roaring as the plane clawed into the air. The ice runway flexed under the weight, and the pilot did not look back. The second flight followed 2 hours later, carrying the remaining personnel and classified documents packed in steel cases. Kerkering was on the second plane, standing in the cargo bay as the loadmaster sealed the ramp, and he watched Camp Century disappear beneath the clouds. Tunnel still lit, reactor vessel still in place, and the ice still moving. By summer 1964, survey teams found the main tunnel had collapsed entirely. Ceiling and floor had merged, and the reactor trench was inaccessible. The PM-2A casing was buried under 12 feet of compressed ice and could not be excavated without cutting a new access tunnel, which would itself collapse within weeks. The reactor was not damaged, it was entombed, sealed by the same glacier it was built to defy. And no extraction plan existed that did not require building a second doomed base to reach the first. Pentagon canceled Project Iceworm in July 1964, citing insurmountable engineering challenges. Ice creep made permanent vertical structures impossible, and no method existed to maintain missile silo alignment over multi-year timelines. The 600 planned silos would never be drilled, and Camp Century's failure proved that subglacial military bases were engineering dead ends. The billions allocated for Iceworm were redirected to submarine-launched Polaris missiles, which required no static infrastructure and could not be crushed by a glacier. The Army declassified Camp Century's existence in 1995, but did not disclose the buried reactor and waste. The base was presented as a scientific research station that studied Arctic conditions, and Project Iceworm remained classified for another decade. Environmental scientists discovered the contamination in 2016 using ground-penetrating radar and ice core samples, finding diesel fuel, polychlorinated biphenyls, and low-level radioactive material from the reactor coolant, slowly migrating toward the coast as the glacier flowed. As of 2025, the abandoned base sits under roughly 100 feet of ice, slowly migrating toward the coast at 15 feet per year. The reactor casing, concrete foundation, and 1,800 gallons of drained coolant remain in place, along with 200,000 gallons of diesel fuel in underground tanks. Climate models predict the waste will reach the ocean by 2090 as the Greenland ice sheet melts, releasing contaminants into Arctic waters with no containment plan and no agreed timeline for remediation. No international agreement exists on cleanup responsibility. The US claims the waste is Denmark's problem because Greenland is Danish territory, while Denmark argues the US military created the contamination without consent and must remediate it. The dispute remains unresolved, and neither government has allocated funding for extraction or containment. The reactor and waste continue their slow journey toward the ocean, and the glacier will deliver them whether the diplomats agree or not. Camp Century's failure reshaped Cold War Arctic strategy. The Pentagon concluded that subglacial installations were engineering dead ends. Plastic ice deformation could not be stopped, only delayed, and shifted investment to mobile platforms that did not require static infrastructure. Polaris submarines could patrol under the ice cap itself, launching missiles from any position, invulnerable to the glacier that crushed Camp Century. The reactor that was supposed to enable a hidden missile field instead proved that deterrence belonged at sea, not under the ice. The PM-2A reactor, designed as a triumph of portable nuclear power, remains the only military reactor ever abandoned in place. It sits 100 feet beneath the ice, a frozen monument to the limits of engineering ambition against geological time. The Army built it to prove that nuclear power could sustain a base anywhere, and it did, for 3 years, until the glacier reminded them that anywhere does not mean forever, and portable does not mean movable when the ice decides to close. Colonel John Kirkering's evacuation of Camp Century was recognized as a successful crisis response. All personnel extracted, no casualties, and operational security maintained. His service record noted the decision to prioritize human life over equipment recovery, a judgment the Army later codified into cold weather emergency doctrine. Kirkering retired in 1972 and never publicly discussed Project Iceworm because the mission brief forbade it, and because some lessons are written in ice, not paper. The Peter Miller rotary saw was recovered during the evacuation and shipped back to the manufacturer in Switzerland for analysis. The blade crack was determined to be a stress fracture caused by cyclic loading in sub-zero temperatures, a failure mode the manufacturer had not anticipated. The company redesigned the blade with reinforced carbide segments and sold the improved model to mining operations, crediting Camp Century's extreme operating conditions with driving the innovation. The saw itself is now in a museum, labeled as the tool that carved a city under ice. Camp Century taught the military what glaciologists already knew. Ice is not ground. It is a fluid on geological timescales, and any structure built inside it will eventually be consumed. The base lasted 3 years because the engineers worked faster than the glacier, but speed is not the same as victory. The ice moved at 4 feet per year, every year, for 10,000 years before Camp Century, and will continue for 10,000 more. The reactor is still there, still migrating, still proof that you cannot outrun a glacier. You can only decide when to leave. The tunnels are gone, the reactor is buried, and the men who built Camp Century are retiring or gone. But the ice remembers. Every winter, the glacier adds another layer of snow, compressing the base deeper. And every summer, the melt accelerates, carrying the waste closer to the ocean. In 2090, according to the models, the first contaminants will reach Arctic waters, and the world will be reminded that some engineering failures are not resolved. They are merely delayed, frozen in place, waiting for the climate to deliver the final verdict on what we buried and what we refuse to clean.